Hello, I'm back. Right. Next incident lesson on confidence interval. You should have two things with you, Matrix. You should have blah blah blah. Something's going on here. Here it is. Sorry about that. Okay. So you should have two things with you. You should have the confidence interval, this table, you should have your, or in other words, your formula sheet, and you should have your blank notes that I sent you, the fill-in notes, and we're working from page 217. I know the answers are just there in your textbook, but if you don't engage with them, it's a bit of a waste of time. Okay. All right, so let's have a look at example 2 to start off with. Okay. So example 2 says, nice and pretty. Right. A random sample of 50 is drawn from a normal distributed population with a standard deviation of 10. The sample mean is 32. Find a 97% confidence interval for the population mean. So what are we trying to figure out? We want to be 97% confidence. What are the boundaries? Okay, that I'm certain, 97% certain that the actual population mean will lie within that boundary. Okay, and we're looking at a distribution of means. Okay, so right, and what does it say? Well, a random sample of 50, size 50 is drawn. Okay, so that is n. So n is equal to 50. It's normally distributed with a standard deviation of 10. So standard deviation is equal to 10. Always be careful if that's variance. Remember, you find the square root of it. And the sample mean, x bar, is 32. Okay, so this is a pretty straightforward one. And I'm working with a 97%. Okay, remember the standard mean here is 32. We want to see our error away from the mean for a 97% confidence interval. Excuse me. So, first thing, let's deal with the problem of a 97% confidence interval. So what's the h of z score we're going to use here? H of z is going to be 0.97 divided by 2, which should be 0.97 divided by 2 equals 0.485. So I'm looking for a z score of h of z score on my table. The area must be 0.485. So if I go to my table, 0.485, 0.485 is right over here. Okay, 0.485, and that corresponds to 2.17. Okay, so I get a z score of 2.17. Sorry, that's one. Z is equal to plus minus 2.17. So that's my z score in the interval for a 97% confidence interval. Right, so now you go to your formula sheet. What's the formula that deals with this? It's this one over here. Okay, so write that down. So the boundaries for mu are upper and lower boundaries, x bar plus minus z sigma over root n. So this is how you're going to set them up, and you're going to say, right, therefore mu is equal to the boundaries of mu, okay, for a 97% confidence interval is going to be 32 plus or minus z score, which is 2.17. That's where the plus minus comes from. Sigma is 10 over root n over root 50. So what I would do in my calculator, remember you always push for time in a hectic manner. So you're going to go 32, okay, 32 plus 2.17 times 10 over root n, so over the square root of 50. This is going to be my upper boundary. Okay, let's do it to one decimal place. So mu is equal to the upper boundary is 35.1. Okay, and the lower boundary of a 97% confidence interval, just go back and change the plus quickly to a minus. and you end up with 28,9. So 28,9, 28,9 and 35,1. It's one decimal place. So with 97% confidence to lie between 28,9 and 35,1. Okay, fantastic. Make sure you understand that. Right, next question. Kevin wants to take Sasha on a romantic summer holiday to Paris, France. He browses on the internet and takes a sample of 36 quotes. So straight away, we know n is equal to 36, right? He assumes that the prices are normally distributed and finds the following. Right, we've got a 98% confidence interval. Okay. And we're given this case our upper and our lower boundaries. Our lower boundary is 2,684. Okay, our upper boundary is 3,616. That's your values of mu for a 98% confidence interval. Right. First question is go find the sample mean x. Well, always remember, guys, okay, that for your mu, you've got a normal distribution here, and there's your lower boundary of mu, and there's your upper boundary of mu because of symmetry. Okay, you can always a little proof if you went lower boundary plus upper boundary divided by 2. Okay, you're going to end up with x bar. Well, what's the proof for that? The lower boundary is going to be x minus z sigma over root n. That'll be the lower boundary. Okay, plus the upper boundary is plus x plus z sigma over root n. Okay, and what happens? That cancels out. Okay, and that's all over 2. So if you add the lower boundary plus the upper boundary divided by 2, you end up with 2x bar over 2, which is x bar. So that's a proof that if you've got the lower boundary and the upper boundary, add them up and divide it by 2, that's the algebraic proof, you get x bar. Okay. Intuitively, you should be able to see. Because of symmetry with a normal distribution, if you add the lower boundary and the upper boundary, you're going to get the sample mean. Okay. So the sample mean in this case, for Kevin, 2,684 and 3,616, okay, were our two, a lower boundary and upper boundary. Okay, so the sample mean, okay, is going to be the middle of that. So it's simply 2,684. So be careful of this, because if you don't recognize this, if you've got the boundaries, that's how you find your sample mean. Okay, just by adding them up and dividing by 2, because so much of the rest of the question, okay, depends on knowing this value. So don't mess that up, guys. So you're going to have 2,684 plus 3,616 over 2. So you should get the sample mean of 3,150 Rand for the 36 things that he looked at, okay, in this question over there. Right. Then the next question says, what did we want? Okay, we wanted to find this population standard deviation. So we're looking, there's space on your next page to pull this in by the way. So we're looking for sigma, all right? What is sigma? So you can work with the upper boundary or the lower boundary for this. Okay, if we work with the upper boundary, our upper boundary is 3,616. If we work with the lower boundary, you don't have to do both, one or the other. It's 2,684. Okay, so this stands for the upper boundary, that stands for the lower boundary. Okay, over there, upper boundary, lower boundary. So the upper boundary is x mean plus z sigma over root n. Okay, so the question now is we've got to go find the standard deviation. So if I plug in my values, my upper boundary is of the mean is, population mean is 3,616. The sample mean is 3,150. Right, now we've got to worry about the z-score. We haven't got that yet, but we're working in a 98% confidence interval. Okay, so in a 98%, all this information This was your confidence interval for 98%, right? Okay, so you got 98%, 0.98 is that area over there. Okay, so your H of Z score is going to be 0.98 divided by 2, which is 0.49. So H of Z is equal to 0.49. That's going to be that area over there. Okay, so we need to find the Z scores that go with that. So you're going to go to your table and look up 0.49. And 0.49 is pretty much here. 0.49, which is 2.33. Okay, I would use 2.33. Remember, okay, if you're a little bit off, it's not the end of the world, right? To 0.49, that's just a fraction over 2.33. Okay, looks right. So for 98% confidence interval, so 98% confidence interval implies that the Z is going to be plus or minus, what did we say, 2.33. So Z is equal to plus or minus 2.33. Okay, so if it's the upper boundary that we're working with, the Z score is plus, that's where we get the plus from. So it'll be plus 2.33, okay, times sigma. We're looking for sigma. N is 36, so over root 36. Okay, so to work out sigma, you're going to go 3616 minus 3150 equals 466. Then you've got to times it by root 36, which is timesing by 6. And then you've got to divide by 2.33 equals, and we get a standard deviation of 1,200. If you use the lower boundary, you get the same thing. So here I'm going to you go 2684 is the lower boundary, is equal to the mean, which is 3150. But now you have a minus sign, 2.33 sigma over root 36. Okay, and if you want to check, you can go check that out, but you'll get the same answer. Sigma is equal to 1,200. So when you're finding sigma or n, either go use the upper boundary or the lower boundary. You don't have to use both. Okay, right. So that's B. Sigma now we know is 1,200. Okay, the next question says, okay, determine a 99% confidence interval, okay, for the average hotel price per night. So, what are our parameters? Okay, well, we've got sigma now is 1,200. Okay, we know that the sample mean is 3,150. We know that n is equal to 36. But now we want a 99% confidence interval. Okay, so for a 99% confidence interval, we're looking, that whole area is 0.999, but we want the blue area. So H of Z is going to be 0.99 divided by 2, which is 0.495. So on my table, I've got to go look up 0.495. And if I go to 0.495, with this one over here, 2.576 is what we normally use. It's between those two things, 2.576. So I'm going to use, for a 99% confidence interval, that is plus or minus 2.576. So that Z score would be negative 2.576. That's 2.576. That's your Z score over there. Right. So now I've got all the parameters I need. Got Z, that, and I've got the formula. Okay. So mu is going to be equal to x bar, which is 3,150, plus minus Z, which is 2.576, okay, times by sigma, which is 1,200, over root n, which is root 36, or you can just write 6. Okay, so pop that into your calculator, and you're going to go 3150, try to get used to working quickly, plus 2.576 times 1,200 over root 36, which is 6. So the upper boundary is going to be, so mu lies between 99,3665,2. It should be more spread out than the other interval because we're getting more accurate. You can see the upper boundary is more spread out than the original upper boundary for a 98%, not much because there's not much difference, only 1%. And the lower boundary, keep the calculator, that on your calculator screen, quickly scroll back and change the plus into a minus, ka-ching, and you get 2634, which is what we expected, a bit more spread out because we want to be more accurate, and I get 2634,8. 2634,8, so I'm 99% confident that the mean price of a hotel room lies within that interval over there. Okay, good stuff, good stuff. Right, and last one for this, quick example 4. All right, it says, right, there we go. The downloading of an online HD movie is very popular, blah, 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 but they reckon that the average movie size is 1,500 megabytes, okay, with a standard deviation, okay, of 500 megabytes, okay, assuming a normal distribution, okay, so they said, they guess that mu is that, right, roughly right about there, with a standard deviation of 500 megabytes, assuming a normal distribution, how large a sample of movies needs to be downloaded? So we're looking for a sample size n to be 95% confidence, okay, 95% confident, okay, that the estimate, in other words, the error, is equal to the difference between the mean and the sample mean is within 100 megabytes. Okay, so we're looking at error. So this kid guesses it's a certain amount. We actually don't even need that value. Okay, that value doesn't affect things. Basically, now, if we're working with a standard deviation of 500, and we want a 95% confidence interval that the error is within 100, okay, regardless of what the mu is, go find what must n be. So what gives you your error? Well, remember your formula. If you go to your formula sheet, okay, you've got mu is equal to the population parameters, the parameters for the population mean are as such. So remember, if I went mu minus x, okay, which would be equal to plus minus z sigma over root n, this, if I want to think of that as your that's your error. This over here is your error, but if I really want to just think it as a distance, in other words, as a positive value, I can say that. So you can just look at the positive values. You can see in the textbook what they do. They don't really use absolute value signs, but I think of it like that. Okay, so that is your error over there. Okay, and it's determined. Okay, remember the bigger sigma is, the bigger your error, the bigger your population size, the less your error. Okay, and the bigger z, okay, then the interval will be bigger because it's going to be more accurate. So that's the principle we're going to use over here. So in this case, my error is 100 megabytes, right? So my error, mu minus x, must be equal to 100. Okay, but we know that the error corresponds to z sigma over root n. Okay, well, we've got sigma. Sigma is equal to 500. The problem is, okay, we don't know what z is, but we were looking at a 95% confidence interval. So for a 95% confidence interval, if you forget it, remember that's 95%. Half of that is your h of z score. So 0.95 divided by 2 is equal to 0.475. I'm looking for an area of 0.475, and that's the one that gives us a nice number, if you remember. So if I look for h of z is 0.475, 0.475, that should be, sorry, 0.475. I'll go find 0.475, remember it's this one over here, the nice one, and 0.475 is 1.96 z score. Okay, a z score of 1.96. Okay, so I'm going to get z. I'm going to use for 95% confidence interval, z is equal to plus minus 1.96. Okay, but if I put an absolute value, it becomes positive. Okay, so I get 100 is equal to the absolute value of the thing. We don't have to worry about the negative score. It's going to be 1.96. times sigma, which is 5,000 over root n, 500, sorry, 500, 500 over root n. So if we manipulate that, root n is going to be equal to 1,96 times 500 over 100. In other words, root n is equal to 1,96 times 5, 1.96 times 5. So root n is 9,8. So n is equal to, you've got to go square that. And I get 96,04. The question was, in order to be 95% accurate, okay, that he wants to be 95% certain that there's an error of only 100 megabytes, how many movies must he download? Well, 96 won't quite be accurate enough, so you're going to have to round it up. So you must download at least 97 movies in order to be 95% accurate, okay, that there's an error of 100, okay, between the actual population mean and the sample mean. Okay. Righty, get all that down. Right, this one now, guys, with this one, okay, I made a little note here. I chatted to the examiners from St. John's, and she said, this is not really, I had a question about this at one point. She said it's actually not really examinable. But I just want to, I haven't got that cast in stone, but highly unlikely that you do this. The difference with this question is you're actually not given, okay, the actual population standard deviation, which is what you will always be given, okay, I'm guaranteed in the exam. But just in case, let's just do one and one only, okay, where we just have to calculate that. So it said the speed in kilometers of 8 cars passing a camera on the N1 highway recorded as follows: 85 blah 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 blah. Assuming a normal distribution of the car speeds, find a 92% confidence interval for the two average speed. Okay, again, sure. I mean, the sample of 8 is a bit ridiculously small. I mean, it doesn't really tell us much. Okay, but let's have a look. Okay, so the confidence interval should be pretty big. If we have a look here, right, so here, guys, we're not given. Really, in an exam situation, they'll tell you what sigma is. In other words, they'll give you the population standard deviation. But we can find the sample. So this notation S stands for sample standard deviation, as opposed to sigma, which is your population standard deviation. Okay? So we can use an estimate, that's what they're saying over here. Okay, where instead of using sigma in the formula, we're going to use S. And you can find S, okay, on your calculator. So if you're going to do this, if you want to enter this data in stat mode, sure, I don't remember to do this mode, stat, and we're looking at variance number 1, okay, and our scores are 85 equals 115 equals 122 equals 145 equals 135 equals 120 equals 97 equals 125 equals, right? Then you clear it and you go shift 1, and I'm looking for variance. And first of all, the mean x bar is, I don't know if you can see that, is 2. So you go 2 equals, and you get a mean of 118. Okay, right? Then if you clear that and you want the sample standard deviation, okay, just checking if I'm right. Yeah. 118, and you go shift 1, and I'm looking at variance again, and if I look at SX equals, you should get 19,36. Okay, right, if you round it off, 19,36. So you're going to use S as your sigma value in this case. Okay, so that's your sample mean. We're going to use this as an estimate for sigma. Not very good maths. Okay, shouldn't really be an exam. Wouldn't expect it to be, but if by some freak it comes up, okay, then you're just going to remember. So if you're not given the standard deviation, you're just going to use your calculator and get an estimate of the population, of the sample standard deviation, and use that instead of the population standard deviation. Right. So now I've got my parameters. I've got x bar. is equal to 118. I'm going to use a sigma estimate of 19,37. I've got a sample size of 8 cars. All right, the last thing I need to find is Z. To find Z, I'm going to look at a 92% confidence interval. Okay, and for a 92% confidence interval, this is H of Z is going to be 0.46. Okay, and yeah, that's right. Okay, so I'm using H of Z is 0.46. That's half the area. So I go to my table, I look for 0.46. Oh, here's 0.45999, which is pretty darn close. So I get 1.75 is what I get for my Z score. Yep. Okay. So Z, so for this, Z is plus minus, what do we say? What are we looking at? I lost complete track of my mind there. 0.46 was over here, and we said it was 1.75. 1.75. So Z is equal to plus minus 1.75. That's my Z score. Write the formula down. Mu is equal to x bar plus minus Z standard error sigma over root n. So mu is equal to 118 plus minus 1.75 sigma, which is equal to, we're using an estimate of 19,37 over root n, root 8. I would think we'd get pretty big boundaries. So you're going to go 118 plus 1.75. I still got my in stat mode. 118 plus 1.75 times 19.37 over root 8 equals, and I get 129.98 is my upper boundary. So let's just make that 130. Upper boundary of 130. Okay. And your lower boundary, okay, is going to be that minus that equals 106. Okay, approximately. So we're 92% certain that the mean is somewhere between 106 and 130. Pretty spread out. Why? Because n is so small. All right, guys, that's that for today. Okay, nearly getting there. Arrivederci.